Hello, folks. Good morning. Welcome to the 14th edition of the Risk and Resilience Tech Hub seminar series. For those of you who don't know, the Risk and Resilience Tech Hub is a public-private partnership working across Palm Beach, Broward, Miami-Dade, and Monroe counties. The objective is economic development. This is not a research project. We want to reduce barriers to new materials, new technologies related to concrete and coastal solutions, and we want to commercialize these solutions. We are one of 31 federally designated tech hubs. There are three primary projects: Next Generation Concrete, led by FIU, Workforce Development, led by Miami Tech Works, and Governance, led by the county, which is, of course, the overall lead of the project as well. We aim for good jobs, thriving startups, resilient economy, resilient infrastructure, and stronger national security. While the majority of the research that is funded and the efforts that are funded do focus on coastal defense and on concrete materials, energy efficient buildings is also of interest. And ultimately, we aren't just interested in a few points here and there, right? We're interested in this entire water, offshore, inland, with a number of different things related to energy, to workforce, to 3D printing, to novel concretes, to clean concretes, to testing materials for hurricanes. All of those things are of interest in developing our technologies. What you're seeing here, the Sustainable and Resilient Infrastructure series, is just one small part of this entire piece. The objective of this seminar series is really to make these connections happen, right? We want the startups to talk to the companies, to talk to industry, to talk to VC, to talk to the government, etc. We want to educate and bring awareness to high TRL technologies to accelerate their adoption. We want to disseminate information on both high and low TRL technologies to increase the TRL. And we want to establish connections between the various stakeholders. That's the most important part of these connections that we will be establishing. And through that, we aim to establish on advance the startups and technologies that are primarily in South Florida. And for those who are not in South Florida, we hope that they will come to South Florida because of all the nice things that we are doing. Today's talk is going to be given by Leonard Nelson from Natrx. The title is Inviting Water in, the New Logic of Resilient Infrastructure. I'm going to let him introduce himself, apart from saying that he's obviously extremely well established, well accomplished, and he's going to do a fantastic job. The one thing I would ask for you is please introduce yourself in the chat. If you have some nice announcements, make them. If you want to put in your LinkedIn, do that. If you have a request, do that. This is number 14, number 15, 16, and 17 of these will take place in 1, 2, and 3 months. They'll be Dolgo, Canopy, and Primostar, respectively. So with that, I stop. Leonard, it's all yours.
Excellent. Well, Pranoy, thank you so much. And I wore the same shirt when I was getting ready this morning. I picked the same shirt as my bio photo, so truth in advertising there. And really excited to just, get a chance to get to know all of you. And we're really excited to share a little bit about our journey, what we've learned in this field, kind of dig into the problem and just talk about how can we use natural systems and technology to solve the problems that we have in the resilient space. So I'll go ahead and share my screen. And speaking of technology, I'm going to try a new format here, presenting. Can everybody see the screen?
Yes.
Excellent. So just a quick snapshot of us before we jump in and get started. Let me minimize this screen here. So Natrx, we provide technology. We help to activate projects and communities at the interface between the natural world and the built environment. We're very passionate about helping our clients to achieve functional, economic, and environmental benefits at the places they work. The problems are pretty hard. It really is a daunting challenge to even define resilience in the first place and deliver solutions consistently. Doing more with less is kind of a theme in our world, so we'll talk a bit about that. And then we'll talk about how can we use technology to get smarter together as a community. So just a snapshot of our firm. We have about 20 employees. We're technology focused. We're very much We have a lot of horizontal technologies that could be used in other domains, but we really focus exclusively on infrastructure and where land meets the water. We have over 85, probably over 100 deployments globally at this point, commercial large scale deployments. Our technology has its roots in the late 2000s or late 90s, early 2000s. So we've been at it for quite a while. 115,000 modular storm flow and flood control units deployed. We'll talk about some of those. And we've analyzed over 30 million linear feet of infrastructure, waterfront infrastructure with our platform. All that's hard. It's hard to scale. I think we're all working together and learning as a community. So just looking forward to having this dialogue and having a chance to share some of what we've learned. So from a problem statement standpoint, I think everybody here knows, how big and how difficult the challenge is. So most of the world's infrastructure and population are concentrated near a major body of water. That is coastal migration trend is only increasing, and with all the people, it brings a lot of assets, a lot of infrastructure to serve those people. And generally speaking, I'd say we know how to build things, globally, right? We know how to build buildings. There's a lot of modularity. There's a lot of technology, and there's a lot of tools. But a lot of that stops where the built environment meets the water. And things kind of get very manual, get very slow. Progress, gets a lot more expensive. And unfortunately, that is exactly the location where the consequences are the most extreme, right? Economic consequences, even loss of life. So these are kind of major challenges that are really difficult to deal with. And we look at a number like 100 trillion, it's just a massive number. And so how do we be smart about how to manage it? So unfortunately, the way we build today is just not working. We use a lot of impervious techniques with bulk materials. That's 99% of what's being done out there. There's a few technology firms in this world, but most of what's happening at the water's edge is traditional construction. Very costly, very labor intensive, oftentimes environmentally damaging. And what we're fundamentally trying to do oftentimes is block water out, which only speeds it up and sometimes makes those problems worse. And when you look at the scale of infrastructure in the United States, there's at least 11 million linear feet of infrastructure that's directly exposed to the water. And cost protecting, retrofitting, upfitting, building new is kind of in the range. It always depends, of course, but it can be $50 million a mile or more. So it's a challenging place to work. Very, very manual today. A lot of manual design, a lot of manual bulk material manipulation. And so there's a lot of, the flip side of that is there's a lot of opportunity to use technology to be smarter. So when you kind of look at it, like who's our customer, whose problem is this? That's another challenge in this world in that, it's actually a lot of people's problems, right? So you typically have an asset owner or a property owner. They have a lot of stakeholders. There may be other users on that property, particularly if it's public property. But even if it's private property, there's sometimes shared resources when you're touching the water. There's policy, environmental, and regulatory angle. There's practitioners that need to be able to work in that area, work through those regulations, get things done. And so, really, this is a shared challenge, a shared problem. At our firm, we look at our customer and who we serve as individuals that are trying to do more with less. Those are typically the asset owners and the practitioners working together, and then incorporating the input from stakeholders, the general public, and the environment. And we're also trying to ride the wave of new technologies and new suppliers. Titan gave a great presentation, Eric Kohler a few months ago. So there's a lot of materials innovation, but we can't bring those to practice unless we change a lot of other elements about how we build. So, I guess a kind of a simple question about resilience, and people often ask, is like, why don't you just put more stuff out there, right? Why don't we just build bigger? And I think the challenge is that, we have a mindset that's really built, kind of framed around traditional asset development, like building a building. And it's kind of easy to forget, looking at this, for example, this breakwater here, there's kind of ditches on both sides of the road. So you don't want to leave an asset base unprotected like a coastal community. But it's easy to forget that this big breakwater here is actually not an asset. We may look at it as an asset when a county or municipality or someone deploys it. They may go against it. They may treat it as an asset. But from a public sector standpoint, at least, the actual asset, for example, is the house right here, right? So that's what's paying the property tax. That's what's keeping that city alive. There's a family in a home that's working, living there, creating economic value. The other asset is the shoreline, right? So there are species in there. There's fish that can create food, nutrition. There's enjoyment that can drive a lot of economic value through tourism. If you build too much, if you build too heavy, like you see here with this heavy rock breakwater, you're kind of really destroying the actual asset, right? Like there's no access for that person who lives here. They can't walk across and enjoy that shoreline. They can't really fish on it. Oftentimes, they can't even see it because they've blocked off that natural resource. And so we have to be careful not to overbuild and not to underbuild. It's a tricky balance. And a big part of how we can use technology is to find that Goldilocks point between overbuilding and underbuilding so we can maximize the benefit, not only for the individual landowner, but also for society. So, kind of one of the things that I think is a little bit of a catch-22 for our business is that when you look at procurement rules, when you look at the way that large projects are contracted, deployed, and delivered, it's really based on the way that we build vertical infrastructure or buildings, right? So if you're building a building that's, the property owner owns the land, it's sort of a siloed project. It doesn't impact a lot of people externally. If you build it bigger and stronger, it's pretty much always better, right? So square feet is more value, and a bigger beam is better than a smaller beam. And then there's a lot of innovation in this space. And so I think when you look at the overall construction market, it's about $2.2 billion. The majority of that is in vertical infrastructure, buildings, and actual assets like pipelines, roads, bridges, transmission infrastructure. 700 billion, still quite a big market, is in the site civil service, subsurface marine grading, and what I would consider more the infrastructure world. But we're kind of the little sibling here, and a lot of the ways that things are done are really based on how you build buildings and not how you deal with the water, how you deal with wind, how you deal with resilience threats those resilience threats, unfortunately, don't play by those rules. There's also, unfortunately, fundamental constraints in terms of how we build and what we're able to do. Things are getting more expensive, not less expensive. So there's almost always more work that needs to be done and more assets that need to be protected than there is funding to do it. When you look at the labor market and the supply chain, I think that's equally true. Kind of an interesting stats you can see the excavators there on the right moving rock and bulk material. Excavators alone in the United States, there's 1.25 billion excavator hours per year, every year in the United States. And so just to put that in perspective, your average kind of typical cost to operate an excavator per hour fully loaded is about $250. So that puts just the cost, not necessarily the value, but the cost of operating an excavator in the United States, or operating all of our excavators, at $350 billion a year. And so that's twice as much as the entire cloud computing market in total revenues. Salesforce.com and every single other, the tens of thousands of software as a service companies. We're spending twice that much as a society just to keep excavators operating every year. 40% of the excavator drivers are going to retire in the next 10 years. And as we build data centers, we're not able to keep up with the demand for just excavators and just those crews alone. The same is true on the supply chain side. So we've only built 2 to 3 cement plants in the last 10 years. Last 15 years in the United States. We really need to be adding 2 a year just to keep pace with supply. And so we're not creating a lot of new mines. We're not creating a lot of new materials in the plants, new quarries. We have a fundamental supply constraint on our supply chain. And that's driving costs up and making things more difficult to build with traditional materials. So again, begs the question, how do we do more with less? How do we get smarter? Last thing I mentioned is innovation is not non-existent, but I think it's progressing slowly and it's relatively minimal in the subsurface domain, in the water resources domain. And so, there's a lot, again, this is an opportunity as well. There's a lot of opportunity to incorporate technology, incorporate that line of thinking. But it's also challenging, right? It's very difficult to introduce that. Part of that is because we all know in this space that our toolkit and the tools for the job are a little bit too narrow, but the individual incentives, both for contractors and for project owners, it really incentivizes people to kind of tend towards a traditional approach, right? And so one example I kind of like to use is like, if I'm going to jump out of an airplane and go skydiving, I really want to make sure that that parachute is as, cutting edge as possible and very innovative. And it's been updated since the 40s, 50s, 60s, and 70s. I just don't want that to happen on my parachute, right? I don't want to be the first one to test that new system out, right? So there's a bit of a challenge here that we have a lot of empathy for the practitioners in the field that we work with, in that you're not going to get blamed if you go with a traditional approach, and if you go with something newer without doing the math and without doing the work, and if you can't justify it, that's a little bit more threatening, a little bit more scary. And so when you kind of look at this image here in the background, where we land with this kind of traditional approach is, effectively systems that self-destruct, right? So a lot of the problems we have in society today, there's areas that don't have enough water, but we have a lot of areas that have too much water that's moving too fast. And when you look at the design of this auxiliary spillway, you don't even need an advanced degree, you don't need to be a civil engineer to know that it was really expensive to build. This is millions and millions of dollars. There's a lot of bulk material movement and handling to get this done, a lot of engineering work to get these grades and these lines and get everything inspected. And if you look at it, what it's doing is it's speeding the water up, right? So the day you walk off the job site, this solution is the best it will ever be, right? At that point, as that water screams down this auxiliary spillway here, any crack that forms, which will form in this concrete, that water, that fast moving water will attack it, right? And so when you have a problem, you're going to have a catastrophic type failure, potentially with major consequences. And so the building today, it's expensive up front. The consequences for failure on the back end, the stakes are actually relatively high because of that tendency towards more catastrophic failure. And as we learn and share together, we really need to think about ways that we can avoid solutions that are designed like this that self-destruct on their own and reduce in value over time, right? This is much more of a liability than it is an actual asset. So how can we use technology and natural systems to help us build smarter? So at Natrx, we believe that it's really critical to take lessons from nature. Some people say nature is the world's greatest computer, right? So the computational power of all, billions of natural organisms and systems interacting with water and with all types of resilience threats over hundreds of millions and billions of years is really unmatched by anything that humans have done. And when you look at how natural systems form in water exposed areas, what you see is a lot of complexity. You see geometries that are irregular. You see situations where coral reefs, oyster reefs, the Amazon rainforest, water is allowed to flow, but it's slowed down. And so we believe very strongly we can take lessons from nature, incorporate biomimicry to kind of leapfrog what we've been doing since, say, the 1900s, 1970s, the typical building methods we use today. How do we look at nature and then leapfrog what we're doing to get, a factor of 10x better? And as you look at how nature manages water, it's very different than a wall. It's very different than something that's an impervious way of trying to block water out, right? It's distributing friction. There's voids and rugosity. It's a multi-species holistic habitat that also works with sediment, works with water. It can build land. So people often forget the entire coastal plain, everything from South Florida to, say the entire, I live in North Carolina. Everything east of Raleigh is built by these systems, right? There's no rock underneath the ground. It's built by the sedimentary plain. So this is oyster reefs and wetlands and trees working together to grab sediments, drop it in the ground, build off of it, and create very valuable real estate. And so how do we do this? Like, how do we do this at scale? How do we take that construction power of nature and put that to work? That's a really important lesson for us to learn as we go. So, another thing we can do is look at technology. And I did want to share a little bit. I started my career, I had training as an engineer. I went to work. My first major job was at IBM. And I used to sell, first did project management, technical project management, and then moved into selling servers. And in 2003, 2004, IBM was the king. We were $10 billion. Sun Microsystems and HP were our competitors. They were all at $5 billion. So we were the top dogs. And, you know, when I was there in the early 2000s, we began to see Amazon Web Services come out with these, instead of buying an entire server, these more modular approaches to managing IT. And I can remember telling our executive team, hey, this AWS thing is it's kind of interesting and it's only web servers right now. And everybody kind of hand waved that away. Like, nobody's ever going to really put real workloads on the cloud. It's not really going to take off. I could see somebody running a website, but no hospital, the government, the DoD, they're never going to put their stuff in the cloud. And sure enough, over the years, again, IBM was $10 billion and we were the kings. Over the years, AWS was able to use distributed workflows. And really what it is the community, the sharing between the users. So they unlock the ability for the users to make their systems better, open data sharing. And now IBM is only $5 billion a year. So their revenue is down 50%. And Amazon Web Services is $60 billion a year, growing at somewhere between 30 to 50% year over year. So they've completely obliterated the old way of working, the old way of doing things. And so this siloed kind of protected way of working, and moving towards early release, often incremental bets, incremental risks, lots of small modular solutions that can be tested. There's a lot of analogs between how technology has evolved to what we can do in the site civil world and the resilient space. And in Natrx, we're big believers in that. And again, you don't want to test it on your first parachute first, just like most users in the server world. They didn't want to put their payroll system on a cloud server right away. But there are ways that you can move in and incrementally try and deploy technology. And if we share the data, we're going to get a lot faster. And so to some extent, as people look to define the word resilience, I think of it as how fast can we learn, right? How fast can we learn? How fast can we iterate? How much better can we get at telling our stories and being smarter economically, functionally, and environmentally about resilience? And so again, from a technology standpoint, you can see one of our modular technology-informed physical solutions on the right here. How do we get modular? How do we deploy in increments rather than one big bang mega project? How do we measure what we're doing? How do we get updates from the field? Well, how does the contractor feel about it? Is it installing fast? Is it slow? Is it easy to place in the water? Is it safe? We can, with a modular approach versus a big bang approach with, say, heavy concrete pours or big giant aggregate placements, we can learn. We have a lot of degrees of freedom to learn and get better and shorten that cycle of innovation and iteration in order to do a lot more with less. So kind of the path forward, at Natrx, we strongly believe in modular solutions. So moving away from bulk materials that are manually manipulated in the field to repeatable modular solutions. And this is just a small snapshot of some of the different modules that we have, but anywhere from 20 pounds to 12,000 pounds. We need to figure out ways that we can handle waves, flow, and water forces with less material and less space than rock or, say, site cast concrete or precast concrete, avoiding smooth edges, finding ways to reduce water, and kind of move it from the regime of dangerous and destructive into a range where it creates value. And doing that while we're saving costs and reducing manual field work. And we use two key technologies to enable that. The first is our patented advanced manufacturing technology. So this is how we make our modules. This piece of equipment here on the right, as you can see, it's relatively lightweight. We can produce, the exact number, hundreds to thousands of tons per year, per printer, with a relatively lightweight piece of equipment. Looking forward, we really want to make sure that we can move the inventory position of where and how we make these things closer and closer to the point of use. And so we're able to be a lot smarter about the supply chain to get people exactly what they want, where they need it, at the price that works for them for their budget. And again, these do a lot of things for the end user and the end user supply chain and existing contractor. So repeatable modular solutions, fast construction, less unit operations, that allows the end user to save money. It's less impact on the environment. And it helps people to move incrementally away from the bulk materials, which we use billions of tons of in the United States. And then we have a software platform. So as we kind of move towards these modules, how do we help people to make these decisions? How do we use these new tools? How do you get started, right? Where do I start? What do I prioritize? What's my ROI for protecting something? What are the projects that I don't have to do this year that I might be able to avoid or defer? And what's my expected ROI for getting something done? And so, kind of looking, I think, kind of a little bit of a shift here towards iterating towards that optimal water interaction, right? So we shared that, there's kind of ditches on two sides of the road. You can overprotect and overbuild, and that's generally I would say in our experience, what we see is that there's not enough funding to get things done, but oftentimes when funding is available, there's a lot of waste on the projects that do get done, right? There's a lot of overbuilding and there's a lot of incentives that kind of tend people towards that overbuilding tendency. And so there's projects that are not being protected at all, very critical areas. They don't have the data to know that that should be prioritized potentially, or they don't have the funding. And then on the other side, there's areas where things are being overprotected or overbuilt. And the question is, how do we find that Goldilocks point towards the middle, right? So we see projects where from end users that, they might do something like an oyster bag. Oyster bags are great techniques. A lot of us, including our team, got engaged in this world and got started by community-driven oyster bag projects. They can be great in the right environment, but we'll see customers that put out oyster bags, they get blown away, blown to smithereens, and they go out and do it again, right? And so that's just simply too little to do the protective work that needs to be done for shoreline treatment, for example. And then more commonly, you have something that's overbuilt, right? And heavy site civil where there's too much, there's too much aggregates, too much material, and there's value destruction, even the upfront cost, the long-term liabilities, or the destruction of the resource itself. And so finding that Goldilocks point, it's a real trick. And we believe we should be data-driven and data-informed as we make those decisions. And so kind of like to kind of dive into that, or really quick, as we look at that Goldilocks point, one of the things we're able to unlock with new technology, and we're not the only ones, we've got a very differentiated, unique way to make large physical modules for infrastructure. The one on the right you see here, it's about 2,000 pounds. It's a cubic yard. We can print it out in about an hour. We've got multiple print heads at our facility, so we can really crank these things out. And on the left, you can see Carrot Island, North Carolina. This is protecting a really important port and community, Morehead City, Beaufort. And we're able to do it. We're able to get that balance right, slowing that water down, slowing down that wave force, allowing the holistic natural system behind it, which has wild horses, all kinds of critical environmental systems. But that land mass and that sediment's really important to protect the town behind it, right? So we want to have smart geometries in place that allow storms and allow water to be exchanged in normal conditions. We want to slow that water down and we want that sediment to drop and to keep building up that island like it's been building, over the last X number of thousands or millions of years. And so, we can actually put math to this, right? So as we look at water speeds, and we'll talk a bit about waves in a second, the value creation regime is really between 0 and 0.5 meters per second. So if you can slow water down and invite it into your community, any waterfront property is going to have a lot higher value. It's enjoyable. There's all kinds of environmental benefits. It adds to, it just adds to the economic base of the U.S. to have that. If you completely block it off, or if your water's stagnant, you erode, you reduce, or you destroy a lot of the economic value that you pay to live in that coastal zone for the first place, right? So where you really want to be is where water's moving in this slow value creating regime. As you move up, right, it's pretty surprising, but it doesn't take that much in terms of water flow to destroy a building, to move a vehicle out of the way, to where a human can't walk, right, and to where you completely rip vegetation out. So we want to make sure that we can use light systems that can move water down into that value creation range. And this is a computational fluid dynamic model of the lattice. And so we were able to model, okay, if we use one lattice, we can take, if there's an asset here that's protected by vegetation, or maybe there's a road right here, or maybe there's a pipeline, some sort of infrastructure, we're able to move that current up, right, and away from the asset. And in the back side of it, we're able to model, okay, you're down in that blue zone, right? You're down in where you have very slow moving water, you're building sediment, you're building land, right? So by inviting the water in and changing the way it flows, we're using 1/10 less material than trying to build a giant wall here. Number one. Number two, if that system does breach, we're not going to have a lot of scour and weak sediments around it. We're going to have a healthy, natural functioning system with lots of sediment behind it that's encouraged by these modular flow control solutions. So this is a good example of kind of doing the math, getting smart about what we're using. And this allows our clients and their contractors to move past the typical approaches, sandbags, 3-2-1 concrete bags, aggregates. There's a lot of block mattresses out there, and that cuts costs and gives them a better functional outcome. The same goes for wind modeling. So as we look at wind, we want to do is we look at kind of wake driven or in this case, wind driven waves. We want to be able to model it. We want to be able to understand where the wind's coming from. We want to be able to get the right solution for that shoreline. So we've developed geospatial technology that allows us to model the wind flow. We pull in NOAA wind gauges. We look at fetch 365 degrees. We look at all the storm history from the last 20 years. We're able to get it from a 360-degree standpoint. Where's the wind coming from? Where is it intense? What's the frequency? What's the direction? Roughly how big of a structure do you need to actually solve the problem there? And then what's too big and what's too small, right? So it's a prescription for a modular solution that allows you to avoid that tendency to overbuild, which might strain your budget, and also helps you to justify your investment so you're not in a situation where you're completely unprotected. And so again, from that wind model and from other mathematical parameters, we're able to model the waves. Again, that gives you a very quick, very cost-effective, oftentimes in less than a week, we can deliver people a prescription and a typical kind of plan for what they need to do to protect a given mile of shoreline. And then once we do that, we're able to use our dry forming technology to produce modular shapes that we're able to solve these problems with. And to just kind of run through a couple of case studies really quick. This is an example of a modular flow control technique. So you've got submerged infrastructure here, multiple lines that need to be protected. There's 5 million miles of rivers in the United States. A major resilience challenge we have is that as water moves faster, this is actually outside of Houston. So as Houston hardens and a lot more people move to Houston and move to Texas in general, the speed of the water in the riverine systems goes a lot faster. And a lot of buried infrastructure and subsurface infrastructure that is designed to protect, that was designed to have depth of cover, they're now getting blown out. They're getting exposed and they're experiencing a lot of scour. So the traditional technique, as you see on the right, is to really either concrete over or block mattress the entire river bottom. So you're effectively hardening the entire body of water. So there's obviously a lot of impact environmentally. There's also a lot of cost involved with that, tremendous amount of material mobilization and labor. You're also speeding the water up. As you harden that water body, you're speeding the water up, you're making it flow faster. And again, those systems where you get a lot of fast flow tend to fail in catastrophic ways or often are vulnerable to that. So you're kind of moving from something that's you've invested in, you've hardened it, but you may be less resilient in the end. On the left side here, you can see this more modular approach. We're able to model the flow. What that does is we're able to get sediment to flow back onto that asset. We never touch the asset. We never touch the pipe. But we're able to protect it without even touching it, kind of using the natural patterns of water. We keep the biological system completely intact. We're actually creating net positive habitat and structure as we do it. So that's a much better functional, economic, and environmental outcome. So big advantage here. This is an example from that project, $8 million for the traditional approach versus $1.5 million for the Exiform modular solution. Looking at the shoreline kind of modular approach as well. What you're looking at here is a flyover after a direct hit by Hurricane Laura. So this was a Category 4 hurricane. By many measures, this is one of the strongest hurricanes to hit the United States in recorded history since we started taking records in the 1800s. Massive storm, direct hit. And on the right side, you can see traditional rock breakwater. So that's a bulk material driven, pretty costly solution. You can see the shorelines behind it is disrupted and eroded. and blown up. The rock breakwaters themselves had to be repaired. The rock was scattered everywhere. That was 10 tons per linear foot. The Natrx solution is 1 ton per linear foot, so 1/10 of the material. Not one of our modules moved. The shoreline itself was completely intact. So this is a better functioning holistic system, not just the module, but holistically overall. The wetlands are more healthy behind it. The shoreline's more intact. There's a better sandbar behind the structures that actually help to build it. And overall, it's a smarter, more functional system. And so with that, the environmental side is fairly obvious, but just to kind of touch on that, when we have a reduced footprint that's designed and inspired by nature, that uses a lot of the geometric cues that we find from nature, so voids, roughness, no flat surfaces, a good degree of water exchange, you inherently, with that geometric complexity, in that water interaction, you inherently build more biodiversity, right? So we've had the chance to study a lot of this, evaluate this with a variety of techniques. We're a big fan of using environmental DNA and a lot of quantitative monitoring to get snapshots of what's going on. But with that additional complexity and water interaction, you're seeing increased species richness over more bulk material driven solutions that depend a lot on, mined sand, a lot of mined aggregates. That can kind of block nature out, block water out. And again, that kind of destroys the natural resource that you're trying to create. And so one of my favorite project examples this is a project up in the Middle Peninsula. So this was an actual homeowner solution. We do a lot of work in heavy industry and public sector, but we also serve individual homeowners as well. When we first started at this site, you could reach your hand. The shoreline was that wetland platform. You could reach your hand underneath the marsh platform. It was so undercut by the consistent erosion, and almost put your whole, your head and your arms underneath the edge of the marsh platform. And because of all that erosion, it was smelly and mucky, and there was just lots of stagnancy and mosquitoes, and just smelled bad and looked bad. And so we did a lot of modeling. We got the right size solution here, and you can see kind of from this drone footage that, SAV lighting up, the marsh platform is really healthy again. We've completely stopped the erosion. The property is beautiful. It's a much better place to experience, right? So if you're a homeowner, you want to be able to experience that shoreline, fish it, play with the children, play with the grandkids, and enjoy it. And if you use a rock solution that's 5 foot above mean high water, which some of the neighbors here have done, you can't even see the water from your property. So we're really proud of a lot of these, not just from an environmental side, but the delivered functional benefit and the economic benefit of that delivers our clients. And so I wanted to quickly, before have maybe 5 minutes here, kind of show you some of the software that we're able to deploy to our clients in order to get started. One of these is at a large scale land loss. So North Carolina has $100 billion of coastal assets, but the state is unaware of exactly where we're losing land. So one of the things we often do when we start with large scale energy clients, ports, and municipalities is, where are you losing land and where you're gaining land? And if we're able to zoom in to, say, Morehead City, which is where that Carrot Island project is, a lot of our clients and practitioners don't know that information of where do you have these resilience risks. And if you have, there's a port, there's all sorts of residential infrastructure, there's critical roads. And if you are losing land near a major piece of infrastructure, like Highway 70 here is really critical. So if you've got a point where you're losing land near that asset, you might be able to make a better decision to prioritize that up front with a nature-based solution. Potentially you can solve that with something that's lightweight and modular for $500K, rather than waiting until you've lost the land, a hurricane hits it, and now the whole road caves out and you've got a $50 million solve. And so that's how using data is really helpful for making good decisions, getting ROI up front, kind of figured out, prioritizing, and really using data to understand how do you use your resources most effectively, and how do you stack up your projects, and how do you get on a platform of kind of rolling net positive ROI solutions as you go. I also wanted to kind of move through. We do a lot of what we call action pages. We find, again, that these solutions are oftentimes, it takes multiple partners, right? So when you look at, we're working on a big coral reef off the coast of Hawaii. So this is a good example of habitat as infrastructure. Coral reefs are a major economic driver for Hawaii, obviously. And we're pulling together academics, conservation groups, the State Department of Aquatic Resources. There's federal funding involved. There's private sector entities, and we're pulling it all together. And we're using data to tell the story and to get better at how we deploy these things. We're able to kind of work with these various practitioners to share and kind of open source the geometries we're doing, how we're doing it, as we do it. And from projects like that to even kind of more standard, living shoreline treatments, as we work with multiple partners, in this case, a levee district, an energy firm, various other conservation groups. Uh, you know, what works where? What is the natural systems response? Um, how do the community partners feel about it? What are we seeing? So this is a good example here of very storm impacted infrastructure. So the marsh platform in front of this levee before Hurricane Ida was protecting the levee itself. There's 5,000 people that live inside this levee system that, their lives are at risk if that levee is breached. And you can see how bad Hurricane Ida disrupted that marsh system. And so this is an area that's, it's not New York City, it's not Miami. And so how do we come up with solutions that are cost effective, modular, and allow them to kind of regrow that marsh, protect the existing marsh fringes that we have? And as we learn, as we see benefits, both from an environmental side and a functional side, are you building sediments? Are you increasing biodiversity? Are you attracting wetland birds that help to drive tourism? What is going on with fisheries? We're able to use techniques to identify some of those lessons learned, identify some of the biological response, look at the economics, and then share that back out with our stakeholder community so they can get smarter about what they do. And just like Amazon Web Services, we want our customers to get smarter because they're helping us. They're informing us with what they need. The smarter our ecosystem gets, the better we can be as a infrastructure materials provider, providing smarter geometries, smarter solutions, and getting the materials where they need to be to solve those problems. So with that, I'll don't have a ton of time for more software demo. I'd like to kind of dig into a lot more of that. But definitely want to encourage everybody to get started. If you go to our website, you can find our webinars behind getting started. That's a good way to kind of learn more. We do a lot of technical info sessions, so we're learning very quickly from our customers and our stakeholders. We love to do kind of one-on-one info sessions. And then we view a lot of these, with our geospatial platform, it doesn't cost a lot. Oftentimes it can be free to just we call it kind of starting your scrapbook, right? So where's your location? What's your challenge? What are you dealing with, right? So when we first started with Second Turn in the levee district, we didn't have a solution. We didn't have any money to do anything with, but we kind of started that digital scrapbook. This is the location. This is what's going on. We did a small pilot with 3 or 6 units. Then we tacked on another couple hundred units and another couple hundred more. So over the years, since 2021, we've been able to incrementally move through, help them arrange for funding, help them to get smarter what they're doing, save some money, save some labor, and continue to build that out incrementally. And so we're really excited about that kind of an approach, and would definitely encourage all of you to kind of reach out, get the conversation started. My contact information is here. Brandon Corsentino, who many of you might know, he's our director of strategic partnerships. So that's his phone number. So definitely leave that up there for you. And with that, I will kind of turn it back open for questions.